Thank you. And so good morning, everybody. And I would like to thank the organizers for giving me the opportunity to present our work on behalf of my co-authors. And I acknowledge the contribution and support of some institutions here. So before starting, I would like to remind you a little bit about HIV drug and resistance. And very important, especially in the context of this session, is to understand that resistance is an evolutionary process. And the usual pattern for this process is primary resistance mutations that impact the viral fitness negatively. And they are often or generally followed by secondary resistance substitutions that compensate for this fitness impairment. And also very important is to realize that de novo resistance substitutions have been described against every single antiretroviral drug that has been designed so far. And today I will be focusing on integrase inhibitors, which are the newest class of antiretroviral drugs that have been developed. And it is composed of 3 approved integrase inhibitors so far: raltegravir, elvitegravir, and dolutegravir. And of course, as expected with new drugs, we have new resistance mutations that are emerging. And this is just an example. It's by no means exhaustive of the various substitutions you can find upon virological failure with raltegravir. And so you have different integrase substitutions that can emerge, and they're often accompanied by reverse transcriptase mutations that confer resistance against the reverse transcriptase inhibitors that are prescribed or taken with the integrase inhibitor raltegravir. And all this is in treatment naive. And we have a similar situation with elvitegravir with various substitutions in integrase and reverse transcriptase, sometimes reverse transcriptase only, and most often dual resistant, again in treatment naive. So what is really surprising, what is really striking and quite extraordinary is that for dolutegravir, there has been not a single resistance substitutions that has been described to emerge de novo in treatment-naive individuals who have been treated with optimal dosing of dolutegravir. So these results are presented in particular in 3 major clinical trials, and since approval, these results have been consistently the same. And I draw your attention to the fact that you don't find resistance substitutions in integrase, but also you don't find resistance substitutions in reverse transcriptase. So, however, dolutegravir is not totally immune against resistance, and you have this selling trial in which 4 participants have experienced treatment failure. So they were highly treatment experienced participants, but they were integrase inhibitor naive. And so 4 of them developed resistance substitutions. And I want to focus a little bit on this selling trial, which has been published in the Lancet a couple of years ago. What was interesting for us was the high prevalence of the R263K substitution found in 2 out of these 4 individuals. And at week 24, there were 1 case of R263K and then a mixture here. And what was again striking, and which was in contrast to what we observed with raltegravir or elvitegravir, was that their sequences were stable over time. So for an additional 24 weeks, these individuals were treated with dolutegravir, and there was no further evolution, and the mixture here was still there. So we, in the lab, we were not particularly surprised by the fact that R263K was so prevalent in individuals who have experienced treatment failure with dolutegravir, because we had shown previously that R263K was very, very commonly selected with dolutegravir in tissue culture selection experiments. And after that, we had went on characterizing R263K, and we have found that R263K negatively impacts the viral fitness, which is not surprising in the sense that it's a primary resistance substitution. However, what was surprising to us was that there was no compensatory substitution that was able to emerge from this tissue culture selection experiments. And so this is, of course, in parallel with what has been shown in the clinical trial, the selling clinical trial. And the defect of R263K is mostly due to the fact that, of course, it impacts the function of integrase, and therefore, when you measure the integration here on the right of HIV viral DNA within the genome of PBMCs, you can see here in black that R263K would integrate the viral genome roughly at 50% of what has been shown for the wild type. And again, there is no compensatory substitution so far that has been described. So this impairment in integration is persistent as soon as the virus develops R263K. And on the right, you just have a control to show that these viruses are good at performing reverse transcription. They're not significantly different from the wild type. But of course, the real question is, why should I care? And why did I stay to this session? And I will tell you why. It's because integrated DNA is actually very important for HIV pathogenesis. For example, high levels of total and integrated DNA have been associated with worse clinical outcomes, whether it is regular setting or during eradication or treatment or cure trials. And also, of course, with HIV DNA, the situation is really different from HIV RNA. When HIV RNA decreases to undetectable level, when people are treated with ART, however, integrated DNA, it's illustrated here, although it decreases initially, it stays for a long time to often detectable levels. So total DNA and integrated DNA can actually be markers of viral persistence. And this leads me to this model. So upon transmission, we know that wild-type viruses are stored inside the viral reservoir through integration. However, what is for us, because we focus on resistance, what is more important is that resistant strains that emerge upon treatment failure can also be integrated within this HIV reservoir. And then we know that because if you reinitiate treatment, a failing treatment, even decades later on, what happens is that these resistant strains will reemerge very rapidly. So this is for us a very, very clear evidence that resistant strains are actually integrated in this reservoir. So now the real question, the $1 million question, is what happens when these resistant strains actually have a decreased ability to integrate themselves? What will be the contribution of a virus containing the R263K substitution, for example, to this viral reservoir? And what we're saying is that addressing this question is very important. And it's very important because it will teach us a lot about what is the nature of this viral reservoir. And I said it's a $1 million question, so if there are founders in the room, we take checks. I will summarize what I just told you. So dolutegravir is the only antiretroviral that has not been associated with de novo resistant substitutions, in treatment naive. In treatment experience, there is a high prevalence of R263K, and there is no compensatory substitution so far that has been described for this R263K substitution. And this substitution also impairs viral fitness and decreases HIV DNA integration with potential consequences for the reservoir. And of note, I would tell you that this is not only speculation, because the next speaker, the next speaker will show you evidence that variations in the integrase sequence can actually influence HIV pathogenesis. So this is very important. And I would like to finish by acknowledging all my colleagues and, of course, Mark Wainberg for his support, all collaborators. Maybe I forgot some, I'm sorry. And I encourage you to come see me at my poster, 67, but also please have a look at our colleagues' poster on 68 today, which described another individuals who have developed R263K against treatment experienced individual. And I will take some questions, please.